So, welcome students in lecture 4 of magnetic property of the material. Those students are watching first time, they are advised to watch early lectures and to subscribe the channel, and also please share to your friends or relatives. So this is the topic magnetization and magnetic intensity. See, if you see the earth or universe, so it is made of variety of materials or compounds, and each possesses magnetic property that we already mentioned. So if you want to categorize depending on the magnetic nature, we should know something about the material, then we can categorize. So some physical quantity related with the magnetism, if you know that thing, then one can find application of that material. Suppose you want to make the magnet, then what should type the material so it can be used to prepare the magnet. Sometimes we don't want magnetic nature, then what is the nature of that material also? Okay. So why magnetization first of all? What is the origin? Of magnetic property? So if you see current loop, you can say the current is flowing in the loop, so it gives the magnetic field. But if it is a solid, then you cannot see any current, and even it shows the magnetic property, suppose permanent magnet. So if you see the microscopically, we can say that orbital and spin motion of electron gives magnetic property. To any substance. It may be natural or it may be man-made or artificial compound. So basic માં છે ઇલેક્ટ્રોનની ગતિ, સ્પિન મોશન અને ઓર્બિટલ મોશન. Suppose material is in bulk, suppose this is material. So there are so many atoms. So એક atom અહીંયા છે. So this is the atom. In atom there are many electrons. So એમાંની એક ઇલેક્ટ્રોનની વાત હું કરું. Suppose this is atom. So in atom there are so many electrons are revolving. Suppose one electron is revolving here, other one is here. Here is the nucleus. So many electrons. So each this loop is considered as a current loop. તો એમાંની એક લૂપ આ છે ધારો કે. So because of electron is moving in circular path, so you can say the current is flowing in this direction. Electron flowing in this direction, moving in this direction, so current is flow. So we have magnetic moment depending on our direction. You can find the direction. So this is the magnetic moment because of this electron. You have magnetic moment because of this electron. So if you add vectorally, so vector addition of magnetic moment So vector addition of magnetic moment due to motion of electron. Gives net magnetic moment. That is of atom, and if you add all this atom, it become bulk. Okay, so I write it gives net magnetic moment. So any bulk material may have net magnetic moment or may not be. May not be. The net magnetic moment per unit volume is called magnetization. It may have net magnetic moment, it may not be. Sometimes it may not be, but in the presence of external field, it may have. So this totally depends on types of the material. Some materials behaves as a magnet in the presence of the magnetic field. Many materials doesn't give response to the magnetic field. So it totally depends on that property. So that we want to study. So this we can write as magnetization is equal to m net divided by volume. M net is the vector sum of the magnetic moment due to each electron and therefore due to each atom divided by total volume, this volume of this. So this unit of M net we know is ampere into meter square. So dimensional formula is AL2. And M is becomes like this, ampere into meter square divided by meter cube. So it becomes ampere per meter, and therefore dimensional formula is A L minus 1. Okay. This depends on types of the material, also depends on the temperature. Same material but at different temperature it has different magnetization. Okay. Now we want to study the material. અમારે એક મટીરિયલ છે મારી પાસે, એનો મારે સ્ટડી કરવો છે. તો એના માટે આપણે શું કરતા હોઈએ છીએ? એના માટે આપણે આવી રીતે એક સોલેનોઇડ લઈએ છીએ. This is the solenoid. You know the solenoid? Okay. We pass the current in the solenoid. That current is in our hand how much to flow. That is called free current. આમાં જે current flow થાય છે શું કહેવાય ને? Free current કહેવાય. So what is the magnetic field inside the solenoid? So we know the formula B equal to mu 0 and I. I say it is B0. N is the number of turns per unit volume length, magnetic field inside the solenoid. B0 is equal to mu 0 and I, where mu 0 you know permeability of vacuum, N is the number of turns per unit length, so total number of turns upon length, and I is the current through solenoid. Okay, current through solenoid. I say this is one, and now I enter a material which is to be studied. જે આપણો કોઈ બલ્ક હતો, સપોઝ યુ હેવ આયરન, તો આયરનને અંદર એન્ટર કરવાનું. This is one rod. So because of the presence of this rod, magnetic field will change. It depends on, magnetic field depends on the medium. આની અંદર medium કોણ છે એના પર ડિપેન્ડ કરે. વેક્યુમ તો μ0, પણ જો આ મીડિયમ અંદર સોળિયો છે તો બદલાઈ જશે. So now B is equal to B0 plus BM. B0 is this one and BM magnetic field produced because of the rod. આ પોતે મેગ્નેટાઇઝ થઈ જાય છે. આ મેગ્નેટાઇઝ થઈ જાય છે, અંદરનું ફિલ્ડ બદલાઈ જશે. So total field now becomes B equal to B0 plus BM. What is BM? In the presence of, right statement, in the presence of a rod, magnetic field inside solenoid, where BM is the magnetic field due to rod. Okay. Now, what is BM? What is BM? That is because of the magnetization of that. હવે BM આવ્યું ક્યાંથી? તો કે BM is produced because of this magnetization. And how M and B both are related. M is the magnetization and B is the magnetic field. Remember, M is the magnetization, magnetic moment per unit volume, and BM is the magnetic field. So here BM is given by BM is equal to μ0 into H, mu into M. So this is the relation between magnetic field and magnetization. This is SA2 and this is SA3. Okay. Now, up to is okay. Now we are going to define one more physical quantity which is more convenient. હું તમને અત્યારે કે more convenient તો એના પાછળના કારણો છે, તમારે એક્સેપ્ટ કરી લેવું પડશે. In this theory, something you have to accept. Okay, બધું આપણે નથી કરી શકતા. So one more convenient parameter, the magnetic intensity, એને કહેવાય છે magnetic intensity, is more convenient physical quantity is defined as H, it is called H. H is equal to B upon μ0 minus M. H is defined as B upon μ0 minus M. This is definition, magnetic intensity. What is in fact actually? Okay, free current per unit length. Actually H is equal to IF upon length. Side માં લખી રાખું છું, and it is called small IF. This is nothing but small IF. Side માં લખી રાખજો તમે. Okay. So if you use this here, then what you will get? આનો આપણે અહીંયા use કરવો છે. So from equation 4, what we write? So H plus M. H plus M is equal to B upon μ0. And therefore B is equal to μ0 H plus M. H is the magnetic intensity and M is the magnet. It means that both have same unit, and you say this is nothing but ampere per meter. And we have already shown unit of M is ampere per meter. Unit of M is ampere per meter. We already shown it. Let us say this is equation 5. Okay. Now M and H, how they are related? M and M, H એની વચ્ચેનું શું રિલેશન છે? Magnetization is related with magnetic intensity. મેગ્નેટિક ઇન્ટેન્સિટી બહારથી આપણે કરંટ આપીએ એના ઉપર એમ ડિપેન્ડ કરે છે. તો એ શું છે? તો M is equal to chi H, where chi is called magnetic susceptibility. Magnetic susceptibility. And it is unitless. Why? Because H and M has same unit. Ampere per meter, cancel. So chi is unitless. And this depends on types of the material and also on temperature. Susceptibility temperature पर depend करे छे, material पर तो depend करे छे. So from equation 5 what you can write? So B is equal to mu 0 H plus chi H. So we get mu 0 1 plus chi into H. This whole quantity is called mu H. So where mu is equal to mu 0 1 plus chi. Okay. So this is also one more equation. B is equal to mu H. B0 is equal to mu 0 H. B is equal to mu 0 H. If magnet B0 is equal to mu 0 H. So this is called, mu is called permeability of material. And mu upon mu 0 if you write, then it is 1 plus chi. And this is called relative permeability. This is called relative permeability. It is unitless. Permeability. This is unitless. Mu has unit. Mu 0 has unit. Mu has unit. Mu 0 has unit. Chi is unitless. And mu r is also unit. Because chi is unitless, so mu r unitless होना चाहिए. So this is again I repeat. See, why magnetic property? Because of the orbital spin motion of the electron. If we add all this magnetic moment because of the electron's motion, it gives net magnetic moment. Net magnetic moment per unit volume is called magnetization. M is equal to M net upon V. Then we discuss different units. If you have a solenoid, then magnetic field is equal to mu 0 Ni. And in the presence of this rod, magnetic field change B0 plus Bm. Bm is magnetic field produced inside the rod. Okay. So what is Bm? So Bm is equal to mu 0 M. Bm is equal to mu 0 M. And one more physical quantity we define, that is H, B upon mu 0 minus M. Then we have simplified M this side, so it becomes plus B upon mu 0. So mu 0 H plus M. Again, what is H? Relation with H and M. So M is equal to chi H. Chi is called magnetic susceptibility. You have also electric susceptibility. So we specify it is magnetic susceptibility. So we put it here back. So we get B is equal to mu 0 H plus chi H. H is common, 1 plus chi. This whole quantity is called magnetic permeability of the material. So B is equal to mu H. And mu is equal to mu 0 1 plus chi. So mu upon mu 0 1 plus chi. So mu r is equal to 1 plus chi m. Relative permeability. It is unitless. Okay. Now look at here. જે part discussed નથી થયેલો ટેક્સ્ટની અંદર. તો B0 તો આપણે અહીંયા કીધું μ0 ni છે. B0 is equal to μ0 ni, where I is this free current. Now Bm is also, we have current, magnetic field. So this magnetic field must be produced because of some type of motion of electron inside this rod. Bm જેને કારણે પ્રોડ્યુસ થયું છે એમાં પણ કોઈ ઇલેક્ટ્રોનની મોશન હશે. આ જે બ્લુ કલરના રોડમાં એ જે કરંટ છે એ કરંટને કહેવાય છે મેગ્નેટાઇઝિંગ કરંટ. એને શું કહેવાય છે? મેગ્નેટાઇઝિંગ કરંટ. ઓકે, બીએમ જેને કારણે પ્રોડ્યુસ થશે એને શું કહેવાય છે? મેગ્નેટાઇઝિંગ કરંટ કહેવાય છે. તો આ જે કરંટ, this current is current flowing through the solenoid, and this current is flowing in the, we can imagine it flowing through the solid. So this is the magnetizing current. So this is μ0 and common I plus IF. So B is the magnetic field because of the presence of the rod. μ0 is the vacuum permeability and the number of turns per unit length, and I current flowing through the solenoid. And IM is you can imagine the current flowing in the solid material. Okay, so this is called magnetizing current. Remember, this is called magnetizing current. And this quantity is called H. H is equal to Ni, magnetic intensity. H is equal to magnetic intensity. Okay. So, what happens if bar magnet is cut into two pieces, transverse to its length and along the length? So this part we have actually discussed during the theory. So suppose you have, this is the magnet, and if you cut, okay, I have magnet and we cut this magnet lengthwise like this. So in this case magnetic moment will be half of the initial, that we already discussed, so I am not going in details. And pole strength is also dividing. Pole strength is also becomes half. Length remains same. And if you cut transverse, so now length is half, pole strength will not change, and magnetic moment becomes half. Okay, length remains, so length becomes half, and therefore magnetic moment becomes half. Here pole strength become half, and therefore magnetic moment becomes half. Okay, then second one, a magnetized needle in a uniform magnetic field experiences a torque but no net force. So when you put a needle in uniform magnetic field, suppose this is the needle, so north side, south side, and it is placed in uniform field. So force experienced by the north pole, in this direction, and here it is in south direction. So this both forces are equal, as we know, because pole strength is equal, but both are in opposite direction, so resultant force is 0. But both forces are not collinear, so torque is acting. An iron nail near a bar magnet, so suppose now it is a bar magnet and we put one nail. Okay, so this bar magnet produce non-uniform magnetic field, and therefore what happens, because of this north and south there is a field, and here field is different, here is field different, and because of that force also different. Force is different, so resultant force is not 0. So resultant force is acting, as well as maybe this non-collinear બની શકે, તો torque भी લાગશે અને force भी લાગશે. Must every magnetic configuration have a north pole? Not necessary. So what about the field due to the toroid? The toroid means that you cannot say there is a where is the north pole and where is the south pole. It is relative. So when current is passing, one side become north, this side south. But compared to this is north and this is south. This is south, this is north. So you cannot say this is the north pole and south pole in the toroid. And last one, two identical looking two bar A and B are given, one of which is identified and known as the magnetized. Okay, how would you ascertain whether or not both are magnetized? If only one is magnetized, how does one ascertain which one? તો તમારી પાસે બે પીસ આપેલા છે, એક છે મેગ્નેટ છે અને બીજું નોન મેગ્નેટ છે. તો હું કઈ રીતે કહી શકું આઈડેન્ટિકલ હોય તો કયું મેગ્નેટિક છે નોન મેગ્નેટિક? તો how I can say? Suppose I bring this in contact with this one. હું એના કોન્ટેક્ટમાં લઈ આવું. Okay. When you bring in the contact with this, okay, હું એને કોન્ટેક્ટમાં લઈ આવું અને જો અહીંયા સ્ટિક થઈ જાય, if I take here then also it sticks, if I take other part then also stick, it means that this is magnet. કારણ કે અહીંયા કોઈ પણ જગ્યાએ સ્ટિક થઈ જાય છે. પણ જો આ મેગ્નેટ હોય ને આ મેગ્નેટ ના હોય, સમજો, this is one is magnet, two is not magnet, તો કોઈ પણ જગ્યાએ it will stick. But this is magnet and this will not stick. And જો આમ લોખંડનો સળિયો મૂકી દઈશ, બહાર મૂકીશ, તો it will move toward the end. ઉપર જાય અથવા તો નીચે જાય, depending on which one is the nearer one. તો આ નોન મેગ્નેટિક બન્યું, આ મેગ્નેટિક બન્યું. સમજમાં આવ્યું? જો આ મેગ્નેટ હશે તો કોઈ પણ જગ્યાએ સ્ટિક થઈ જશે, અને આ જો નોન મેગ્નેટિક આ મેગ્નેટિક હશે તો એ છેડા ઉપર સ્ટિક થશે. એટલે જેના છેડા ઉપર સ્ટિક થાય એ શું કહેવાય? મેગ્નેટ કહેવાય. So like that you can identify which one is the magnet and which one is the non-magnet. Okay. What is the magnitude of the equatorial and axial field due to a bar magnet of length 5 cm at distance 50 cm from its midpoint? The magnetic moment of the bar magnet is given the same as in example 5.2. So what is 5.2? I don't know. This is 5.2. What is the magnetic moment of the magnet? So magnetic moment you are getting 0.4 ampere meter square. 0.4 ampere meter square. What is the magnitude of equatorial? Okay, it's okay. So this is our magnet, and we are finding magnetic field on the equatorial line and magnetic field on the axis. So magnetic field on the equatorial line is equal to mu0 upon 4 pi m upon r cube. So mu0 is 4 pi into 10 raised to minus 7 divided by 4 pi into what is the magnetic moment? So it is 0.4, and what is the distance? So 0.5 square. Length ની બહુ જરૂર નથી પડવાની આમાં કોઈ. So you can simplify this. 4 pi is cancelled out. So it is 0.4 upon 0.25 into 10 raised to minus 7 r cube. Sorry, I am sorry. I make this correction. This is cube. So still it is 0.5 is multiplied. So if you simplify, so this is 0.4 upon 1.125. So you are getting around 3.2 into 10 raised to minus 7 Tesla. Okay. And magnetic field on the axis, so BA is equal to 2 times that of the equatorial line. So it is 6.4 into 10 raised to minus 7 Tesla. Because here 2m instead of m. Equator was m, તો એક્સિસ ઉપર 2m, સેમ ડિસ્ટન્સ હોય તો આટલું થાય. So at the equatorial line magnetic field is half of the axis. Yes. Okay. You are given this figure. Here is the one magnetic dipole. Another identical dipole is placed at different position. This is Q1 position, Q2, Q3, Q4, Q5 and Q6. Okay. There must have a question, in which configuration the system is not in equilibrium? Equilibrium में क्या रहे? No, तो torque लागे त्यारे. Torque क्या रहे? Maximum लागे. तो 90 degree नो angle बनतो है. कोनी बच्चे? तो कि magnetic field produced by this magnet and magnetic moment of this or that. Okay. So this formula torque is equal to m cross b means mb sin theta. So when theta is equal to 90 degree, you can say torque is maximum for equilibrium manati. So first I draw this magnetic field lines. And magnetic field line avashe direction આમ છે ને, તો આ બાજુ south હશે, આ બાજુ north હશે. So this is the field line. તો દરેક માટે હું ચેક કરું, અહીંયા આગળ થીટા 0 છે, અહીંયા આગળ થીટા કેટલો થશે 0, અહીંયા આગળ થીટા કેટલો થશે 180, અહીંયા આગળ થીટા કેટલો થશે 90 because field line આમ જશે, અહીંયા આગળ opposite થશે 180. So this two position 1 and 2, in position 1 and 2 we have theta is equal to 90 degree. So maximum torque means in equilibrium. So no answer avashe Q1 and Q2. Okay. In which configuration is the system in stable equilibrium? Stable equilibrium means torque is 0, potential is minimum. So theta મારું કેટલું થવું જોઈએ 0. Theta is 0. So potential energy મારી કેટલી થઈ જાય? U is equal to minus mb. And torque કેટલો થઈ જશે 0. તો એવું ક્યાં બનશે? તો અહીંયા બી બને છે, theta 0 બને છે. Yes, theta બીજી ક્યાં 0 બને છે? અહીંયા બે જગ્યાએ. So Q3 and Q6 આના માટે આન્સર આવશે. Q3 and Q6 position, where potential energy is minimum, theta is 0, torque is 0. Then unstable equilibrium. Unstable equilibrium means potential energy is maximum and torque is 0. તો એવું ક્યાં બને? તો જો અહીંયા theta મારું 180 હોય તો torque is 0 and potential energy કેટલી થઈ જશે? theta 180 હોય તો mb. Because cos 180 is minus 1, minus plus. So you क्या बने? Here and here. 180 છે ને? તો આ બે પોઝિશન આનો આન્સર આવશે. કઈ પોઝિશન? 5 and 4. So Q4 and Q5. Where you get maximum potential energy and torque 0. So it is called unstable equilibrium. And third, C question, which configuration corresponds to the lowest potential energy? Potential energy ફોર્મ્યુલા તમારી શું છે? માઇનસ એમ ડોટ બી. તો એ આપણે જોયું બે આન્સર છે એના, એક છે Q3 and Q6. એમાંનું કયું મારું આવશે? તો મેગ્નેટિક ફિલ્ડ પ્રોડ્યુસ એટ ધીસ પોઝિશન, મેગ્નેટિક ફિલ્ડ પ્રોડ્યુસ એટ ધીસ પોઝિશન. તો આ એક્સિસ વાળી લાઈન કહેવાય, ધીસ ઇઝ ઇક્વેટોરિયલ લાઈન. તો એક્સિસ ઉપર ફિલ્ડ વધારે હોય, જો એક્સિસ ઉપર ફિલ્ડ વધારે હોય તો અહીંયા મેગ્નેટિક ફિલ્ડ વધારે હશે, ક્યાં? અહીંયા આગળ. સો મોર નેગેટિવ વેલ્યુ. સો આન્સર ઇઝ Q6. તો આનો આન્સર આવશે Q6. ઓકે. So this is the concept. બહુ સારો ક્વેશ્ચન છે. Magnetic field lines shows the direction along which a small magnetic needle align. It is true. Do the magnetic field line also represent a line of force on a moving charge particle at every point? So suppose this is magnet and these are the magnetic field lines. It is true, north and south. Okay. So if I put magnetic needle, so it always align in this direction. Magnet અહીંયા તો અહીંયા હશે, અહીંયા તો અહીંયા હશે, અહીંયા તો અહીંયા હશે. That is okay. પણ હું ચાર્જ અહીંયા મૂકું છું, so charge is always moving perpendicular to the field line. So you cannot say it is a line of force. In electric field it is true, because force is acting along the electric field. Here magnetic force is not acting along the field. So this is not true. It in a line of force kehavaય nahi. It is perpendicular to the magnetic field lines. Magnetic field lines can be entirely confined within the core of a toroid, but not within a straight solenoid. Why? So in magnetic field line for toroid, suppose this is the toroid. So you can take one closed surface. The number of line entering, same number of line are leaving. So Gauss law is true for toroid, but not within the straight solenoid. Why? So if it is a solenoid, then field line, suppose if you draw like this, magnetic field lines can be entirely confined within the core of toroid, but not within the straight line. Why? So suppose I take so if it is like this, so what will happen? So where it ends? Suppose I take one surface close, then field is coming out from this, but not coming, going inside. આવું possible બને નહીં. અહીંયા તો આવું થઈ શકે. એટલા માટે it cannot be confined. If the magnetic monopoles exist, how would your Gauss law of magnetism be modified? So we know that Gauss law is B dot ds for closed surface. Okay. If monopole exists, then it may be not zero. So I have to add all these magnetic moments, mu 0, into sigma of magnetic poles, all these magnetic poles. અત્યારે તો શું થાય છે, જેટલા નોર્થ એટલા સાઉથ હોય જ, એટલે આન્સર 0 થઈ જવાનું છે. તો એટલું મારે મોડિફિકેશન કરવું પડે. Does a bar magnet exert a torque on itself due to its own field? No, it is not possible. પોતાનું ટોર્ક ના ફોર્સ ના લાગે. પોતાનું લાગે નહીં. Does one element of current carrying wire exert a force on another element of the same wire? Sorry. Okay. તો ટોર્ક એક્ઝર્ટ થતું નથી બીકોઝ સમસમે ઇફેક્ટ કેન્સલ થાય, પણ કરંટ કેરિંગ કંડક્ટરમાં ઇટ ઇઝ પોસિબલ છે. જો સ્ટ્રેટ હોય તો પોસિબલ નથી. મેગ્નેટિક ફિલ્ડ અરાઇઝિસ ડ્યુ ટુ ચાર્જીસ ઇન મોશન. કેન એ સિસ્ટમ હેવ મેગ્નેટિક મોમેન્ટ ઇવન ધો ઇટ્સ નેટ ચાર્જ ઇઝ 0? તો એ પોસિબલ બને કે સપોઝ આઈ હેવ વન સિસ્ટમ એન્ડ there are suppose 10 proton and 10 electrons. Okay, charge is 0. These all are moving in different orbits. So net magnetic moment for each different one. And if you take the vector sum of it may not be 0 also. So charge 0 હોઈ શકે, even magnetic moment 0 ન પણ હોય. એક ઇલેક્ટ્રોન આમ ફરે છે અને બીજો ઇલેક્ટ્રોન આવી રીતે ફરે છે. તો આની મોમેન્ટ આમ હોય, આની મોમેન્ટ આમ હોય, અને બધાનું વેક્ટર સમ કરું તો નો પણ 0 થાય. ઓકે.